Dear ladies and gentlemen, I would like to welcome you to a new edition of BioM Lunchtalk. As we have again English-speaking reference today, the Lunchtalk will be in English. Most of you know that BioM is the cluster management and cluster development company for biotechnology in Bavaria. My name is Andreas Berghammer, and I am responsible for services, cooperations, and sponsoring at BioM. For example, on the PowerPoint slide just now at the beginning, you have seen the announcement for our main cluster event this year, BioConnect. If you would like to participate as a company, please contact us. Today, we are continuing our series on AI ML for biotechnology with two more company presentations, or one company and one pre-seed. AI has rapidly become the dominant topic in many areas. And with this series, we would like to introduce you to interesting companies and organizations that develop or apply AI solutions for biotechnology and can thus contribute to the growth of our industry. Today, we welcome representatives from BioSpire, a research-driven university spin-off project developing new technology in living cell 3D imaging. Specializing in data analysis and optical systems, their technology allows for extraction of insights from clinical data that wasn't possible before. This is followed by an introduction of Cosinus, a certified medical technology company from Munich, easing real-time vital sign acquisition. Numerous patients and medically certified products make Cosinus a pioneer in the field of mobile monitoring. Before we start, some remarks on the format. As always, we will first have a presentation of about 20 minutes. Afterwards, we will have a few minutes for questions, which we will read out anonymously from the question chat because of data protection reasons. You are therefore welcome to post your questions already during the presentation. This will be followed by the second presentation, again with direct questions, and finally a round with our speakers where you can ask questions about both presentations or overarching topics. Please participate actively in the event. We will start with BioSpire. BioSpire has won the M4 award last year, which is a pre-seed competition organized by BioM every second year. Winners are selected in a two-step peer-reviewed process, receive money for 2 years, will hopefully be able to found a company afterwards. Our speakers are Rahmetullah Varol from the Universität der Bundeswehr München. Rahmetullah is an engineer and responsible for the development of the optical system and imaging algorithms. And he's accompanied by his co-speaker, Dimitra Makri. She's an embryologist at the LMU München. Dimitra is responsible for the development of the experimental infrastructure within the BioSpire team. And the title of the presentation is Use of Machine Learning for Microscopic Analysis of Sperm Cells. So who's starting? Rahmetullah, Dimitra?
Thank you for the kind introduction.
We're looking forward to your presentation.
Should be visible now.
Yes.
Again, thank you for the introduction. I am Rahmetullah Varol. I'm a software engineer at BioSpire, and today, together with my colleague Dr. Dimitra Makri, who is the deputy head of andrology lab in the IVF clinic of Ludwig Maximilian University, we will talk about what we are trying to do at BioSpire. And also specifically, we will present a study that we have conducted within BioSpire regarding virtual staining of sperm cells. So let me begin with a problem statement. So one of the important challenges in healthcare currently is the increasing rates of infertility, particularly among men. So over the last 50 years, we have seen a 73% increase in the male infertility rates, and today it is estimated that over 250 million men between the ages of 18 and 50 are infertile. So this rapid increase can be attributed to many factors, but among them, one of the most prominent ones among them are increase in chronic stress, increase in microplastics in the food that we consume, and increase in the use of pesticides. The list can be expanded, but the result is apparent that our infertility rates are rapidly increasing. It is also known that around 40% of couple infertilities are due to the male factor. So, the increase in the infertility of males directly translates to the increase in the infertility rates of couples. So this reality has resulted in a sharp increase in the demand for assisted reproduction technologies, and in other words, the in vitro fertilization therapies. So this is also reinforced by the fact that most couples are now seeking to have children at later stages of their lives. So, however, the success rate of in vitro fertilization therapies are still low. Currently, only around 27 out of every 100 in vitro fertilization therapies result in live births. This therapy can be done in the form of in vitro fertilization or in the form of ICSI, which means intracytoplasmic injection of sperm. But in both of these approaches, you need to select a healthy oocyte, and there needs to be a healthy sperm cell. So the success rate of the therapy itself, it depends on the health of the selected oocyte and the health of the selected sperm cell that is used. We wanted to focus on the sperm diagnostics aspect because over the last 30 years, little has changed in this regard. Whereas in the selection of oocytes and in the incubation of oocyte, there has been a lot of work. So the current state of the art for sperm diagnostics is the use of spermiograms, which means that evaluation of the sperm characteristics, especially the morphological characteristics of the sperm, in a conventional microscope. Spermiograms allow measurement of the sperm morphology, which means the shape of the sperm cell, the sperm's motility, which means the ability of the sperm cell to move around, and also the concentration of the sperm, which means how many sperm cells are there in the sample. However, they lack information about the intracellular structure within the sperms, which means that they cannot see the organelles or the nucleus or the acrosome structure within the sperm cell, which are also very important in diagnosing the sperm cells' health, basically. Furthermore, they also lack information regarding the nuclear status of the cell as well, which means that they cannot assess whether or not the nuclear information within the sperm cell is intact. This information is commonly measured by a parameter called DNA fragmentation index, which tells you the ratio of the single-stranded DNA to the ratio of to the double-stranded DNA. So the measurement of the DNA fragmentation index can be done with fluorescent microscopes, but the problem is that the fluorescence microscope approach is an invasive approach, which means that you need to use a staining procedure to measure this quantitatively. And the staining procedure introduces a cytotoxicity into the cell, which renders this cell unusable for clinical applications. So here you can see a video captured by a conventional microscope that shows the sperm cells moving, and the current approach is that the clinician looks into this conventional this microscopic images and decides whether or not the sperm cells morphology, motility, and the concentration is suitable for the therapy. However, the conventional microscope is insufficient in capturing these important details. So the solution that we are trying to develop in BioSpire relies on the development of a multimodal machine learning pipeline. So this diagram actually shows the vision that we want to achieve in BioSpire, which could also be applied to many other fields in healthcare other than in vitro fertilization once we prove the principles within this limited context. So with this approach, what we do is we capture the information regarding a single cell from multiple modalities. And currently there are three modalities that we are focusing on. The first modality is microscopy data, which gives us information regarding the morphology of the cell. And specifically, we are focusing on the three-dimensional morphology. Also, we can measure the three-dimensional refractive index map of the within the cell. So this gives us an idea about optical properties. And we can also measure the movement patterns of the cells using time-lapse analysis as well. The second modality that we focus on is the immunochemical staining modality, which gives us information about some parameters that are normally invisible with conventional microscopes. This can be the cytoskeletal structure of the cell, the chromatin structure of the cell, or as I mentioned, the DNA fragmentation of the cell. And this measurement is usually done using some stains, some chemical stains that bind to these structures, these subcellular structures, and make them basically shine or make them visible under a fluorescent microscope. And the third and last modality that we are focusing on gene sequencing data, which tells us which genes are being expressed currently within the given sample. So after collecting this information from these modalities, what we do is we train a shared latent space, which can be used to translate between these different modalities. So basically, what a shared latent space means is that it's a structure that encodes the different modalities into a common representation. And this common representation then enables this model to relate the information between across these different modalities. So this means that this shared latent space kind of acts like a dictionary with which you can translate between these different modalities. So such a model can then in turn be used to information about cells that are not visible under a conventional microscope, such as the status of the microscope, is the cell dead or alive, or visualization of the organelles within the cell, or the current cell cycle, etc. So In the specific application that we will present today, we focused on predicting the DNA fragmentation index. So there are some existing studies that in the literature that focus on this problem. And one such example is the work done by McCollum et al. And this was published, if I remember correctly, in one of the papers of Nature. So the name of the journal, specific journal, escapes me right now. But in this study, what they did was they used a pre-trained regressive VGG16 network, and they applied a transfer learning training procedure to fine-tune the model to be able to predict the DNA fragmentation index value that they calculate from fluorescent images they also capture separately. So in order to collect this data, they first fixated the sperm cells beforehand and then captured the bright field and fluorescent images of the whole slides. Specifically, they used the acridine orange test, which gives the ratio between the single-stranded and double-stranded DNA. And with this ratio, as you can see in the slide, you can calculate the DNA fragmentation index. And then they used the trained model to test some untrained or unseen inputs and correlated these values with the real DNA fragmentation index values that they measured. So we used this study as a reference because the data set that they used was publicly available. So we could compare our results with theirs, and we wanted to see the viability of our approach against the state-of-the-art methods. So the approach that we followed was we used an image-to-image translation network instead of a regression network. So an image-to-image translation network actually tries to do what I mentioned in the previous slide. It tries to create a shared latent space that can translate between two different modalities of images. So the main goal of these models is to take an image in one style or one modality and then automatically convert it to another modality. So this method is, these models are commonly used to convert real images into their cartoonified or like stylized versions. But they can also be used in scientific context for quantitative applications as well. And specifically, we use the model called PIX-to-PIX model, which uses this image translation approach and applies it to paired image sequences. So you can use it for particular applications where you have the corresponding images, one image in different modalities. So you can use one image and look at each pixel and translate it into the other modality. So this model has two main parts, as is general with generative adversarial networks. There's a generator part which tries to create images that look like the desired output images, and there's also a discriminator part which judges whether the generated image matches the desired output modality or not. And according to the score that is generated with the discriminator network, the generator network is updated and the training cycle is then completed. In our specific case, the input images were bright field images and the output images were fluorescent images. So here you can see the specific framework that we used for the DNA fragmentation prediction. And we first start with a large bright field image and extract patches that contain a sperm head, which contains the DNA information basically. And then we find the counterpart of these patches in the fluorescent images, and then we create a paired data set that is suitable for training the Pix-to-Pix model. And during the training part, we feed both of these images and train the model. And afterwards, during the testing phase, we only feed the bright field images and compare the output, the generated image, with the actual ground truth fluorescent image. So here you can see some of the generated fluorescent images and their comparison to the real fluorescent images. And from qualitative point of view, the results look quite good because they can capture the pattern of the staining quite faithfully, and they can even, as you can see, they can even capture some small artifacts that have a correspondence in the morphological structure that can be captured with the bright field image as well. So when you see a morphological structure in the bright field image, you can also understand how this translates in the staining pattern as well. Also, looking at the correlation graph, we can see that the predicted and the real fragmentation index values are highly correlated. So here you can see some of the quantitative results of the original study and the models that we have trained. So we trained 3 different models. The first one is a Pix-to-Pix model we trained with the raw images, and then we use the denoising denoising application to clear some of the artifacts from the raw images, and also we use a transformation matrix to better match the fluorescent images to the bright field images. So in order to get rid of any mismatches in the positions of the sperm cells in paired images. And then we used a different model which is called Pix-to-Pix plus, which introduces some optimization into the training procedure. And we compare the results. So the results show that we have seen around a 21% decrease in the mean average percentage error. And we have also seen that the model that we have trained was quite robust to the artifacts in the image. So in a regressive model, you might also be affected by some noise in the background or some artifact that is present in the image as well. But with that image-to-image translation network, you can make sense of these artifacts and filter these out as well. And most importantly, we have seen that a virtual staining approach is also a viable alternative to immunochemical staining for certain cases, especially for cases where the underlying molecular structure somehow translates into the morphological structure that is visible under the microscope as well. So the future steps that we are planning to take and we are working on currently is collection of a custom data sets. For this, we are working in collaboration with the in vitro fertilization center in Ludwig Maximilian University. So we have their project or an effort to collect real clinical samples and collect this rich multimodal data set that will allow us to further the research into predicting not only the fluorescent markers but also the three-dimensional structure of the cell as well. So we are also working towards expanding the model to predict some other fluorescent markers as well, such as the DNA methylation status or the protein status of the cell. And also, as I said, we are trying to predict the three-dimensional structure, the internal structure of the cells as well. So the results that we have obtained with this study is also available in our publication. So you can check that out as well. And yeah, this is all from my side. Dimitri, if you have any other additions, you can also take the stage.
Thank you very much. I think you covered everything, but we are open to questions.
Well, thank you for your presentation. Fantastic work so far.
Thank you.
Let's see. So one question regarding the algorithm. What was the size of the data set?
Yes, so the data set that we have used, as I said, it was a publicly available data set that was published with this alongside this reference work. So in that work, they used 7 donors. So they collected samples from 7 patients, and from each patient, they collected about 150 or so. So in the final data set, we had 274 cell images in the test data set, and around 550 images in the training data set. So in total, we had a bit more than 800 cellular images.
Okay, and you want to use now the real examples in the clinics to extend the data sets, the test, the training, and so on.
Yes, we want to expand the data sets much more to cover much more samples, much more patients, so that at first we are more assured of the results of this approach, and also to cover different cases as well. So a large data set means that you have a lot of variance in your sample as well. So we want to be able to confidently say that this will extend the future unseen samples, unseen donors as well.
And of course, after optimizing the software and the predictability of this model, I think our goal is to probably carry out some clinical studies and actually see in the clinical setting if by using this imaging system and model, if we are able to improve the success rate, which is what our long-term aim is really. So this is where we would be very interested to see in practice what this means. By using data, for example, for the fertilization rate in patients, and even the embryo quality that we can create in the lab, and even for live birth rates, ideally. Mm-hmm.
So will your technology allow then to select individual cells or sperms for fertilization?
This is our goal. This is what we aim.
And is there any idea to what extent you will optimize then EVF?
We hope that we will have at least a 5 to 10% improvement. As Rahmet mentioned in the beginning, 40% of the couples in the clinic are classified as male factor infertility, which is why we hope if we are able to solve at least part of this problem to see quite a significant improvement in the success rates. Yeah.
Another question, how do you want to commercialize your platform?
Yeah. So this is actually one of the points that we are still working on. We are still trying to solidify, let's say. So one approach is to sell this as a software platform to clinics, and there is a lot of interest in this approach, and this has the advantage that the clinics can use the imaging system that they already have, the imaging infrastructure that they already have, and only integrate the software, the software edition that we have into their framework. And another approach could be to work with a microscopy company, a large microscopy company, and integrate our software into their workflow as well. But this is, as I said, this is something that we are working to see which has the better potential.
Yeah, thank you. And well, of course, you're working now on fertility and sperms, but what other application in healthcare could be addressed with that approach, with that technology? What might be other main applications?
So, maybe I can give a quick answer, or Dimitra, would you like to? So one approach that we are also considering is oncology in terms of, especially in terms of assessing liquid biopsies. So as you so the liquid biopsies are getting more popular in cancer diagnostics. One of the challenges in assessing the liquid biopsies, I believe, is for example, assessing the chromatin structure of the cells within the liquid biopsy. For example, the antibody cells within the liquid biopsy to see whether or not they indicate some kind of abnormality. So we could use a similar approach to assess the chromatin structure using a virtual staining approach, only by looking at the morphology of the cells within the liquid biopsy and make predictions about their stages, about their indications into cancer.
Then you need, of course, another model and training sets and new data to
yeah, of course. So yes, that's
for the
true.
software.
Yeah, for so this is a data intensive application, I would say. So for each model, for each parameter that we are trying to measure, we will have to collect some data and train some models for this specific purpose, because we can't say that one model that is trained on predicting DNA fragmentation will work for predicting the chromatin structure as well. So yes, we will have to train a new model.
Okay, thank you. We will move on to the second presentation.
Thank you.
We will see you at the end again. The second presentation will be given by Johannes Kreuzer, founder and managing director. Johannes studied electrical engineering and information technology and completed his doctorate in the field of mobile sensor technology, suitable for everyday use, which also laid the foundation for Cosinus. He has worked in various positions at Airbus, Daimler, Eurocopter, Pilatus, and finally dedicated himself to his favorite subject, mobile patient monitoring. The title is Filling White Spaces in Vital Signs Monitoring. Please.
Thank you. Thank you for the introduction. Yeah, so first of all, a short overview about Cosinus. Cosinus, we founded 2011 in Munich. Co-founder is Greta. And we have our production facilities here as well in Munich. And all the engineering and everything there. At the moment, we are 31 people. And of course, we have several patents and also some protected know-how regarding production processes and algorithms. Yeah, first of all, on the one side, the talk is about AI. On the other side, it's also about vital signs. So first of all, vital signs are the core of every medical assessment. It's core temperature, oxygen saturation, heart rate, respiration rate, and blood pressure, which is normally the beginning of each medical assessment. That's only for the relevance. And when we're talking about Cosinus, we're talking about filling these white spaces. So what are the white spaces in this patient monitoring? And if you're looking at the medical market, there's many segments like the rescue, emergency, the transportation, inside the clinic, after the clinic, as well as the normal GP. All of the segments are trying or are getting spot-wise or sometimes a little bit continuous vital signs, but normally all of this data is lost. So for this, we started to build our own solution, which is on the one side an in-ear sensor monitor, and on the other side the data which is coming from this in-ear sensor. So it's this very small device, the CMID Alpha, which is you can put inside the ear. It's a medical device, class 2A, certificated after the MDR. And it is able to measure the core temperature, the heart rate, as well as the SpO2 level, so the oxygen saturation. And then, of course, we're transmitting the data. And this is the second part of Cosinus. On the one side, we're starting with the in-ear sensors. On the other side, we have the whole IoT solution, Internet of Things, of medical things. So we are able to transmit all the data from the in-ear sensors up to 200 hertz, so 200 data sets per second, to our platform, which is used for machine learning, which is used for studies, but also for normal applications like remote patient monitoring. This is our vision, that it's the continuous data flow, because it doesn't make sense that in each step you will lose all the data what the segment before has. It doesn't make sense. And that's what we are trying to achieve. And now we're talking about the AI and the machine learning. So to get to be able to do machine learning, on the one side, you need data. So this is where we were building up the whole infrastructure. So starting with the data acquisition, in our case, in-ear sensors, but also other medical or non-medical devices where we get the data. Then you need to transmit the data via gateways, mobile applications, or it's depending on where you are, to a server where you have access the data, you are able to store the data. And then, of course, here you can run the algorithms. So it's all the time, if you want to get data, you need to do all the steps, and it's depending on which data it is, which devices you use, and so on. In our case, like I said, the in-ear sensors as well as other medical devices. And why is so essential? And of course, everybody knows it. On the other side, it's often forgotten. To be able to train an algorithm, you need good data. And on the one side, you need it accurate. You need labeled data. You need to know the context information around it. And of course, you need it from different, in different contexts. Mainly, or in optimal phase, it should be real life data and not some specific laboratory data, and as diverse and representative like it's possible. Otherwise, you train all the algorithm for some specific use cases, and then if you jump out of this use case, it's completely failing, or perhaps it's working, you don't know. It's this typical and here it's written in better way, but it's in engineering, it's shit in, shit out. If you have bad data, you can do whatever you want. It will never work at the end. Here is a very famous failure where a trained algorithm from a very well-known company failed, and it was even causing some real difficulties. So where are we using AI and machine learning? On the one side, we use it directly for our own development. So all of the algorithms running in the device. So our goal is always that the algorithms are able to run directly on this small device behind the ear. For this, we use models training on the server and then bringing them down to a algorithm which is able to run on this small microcontroller in a very power efficient way. And on the other side, you need medical certification, and so it has to be also part of this medical certification process. So we, for example, here the SpO2 algorithms, so calculating out of the raw data, the oxygen saturation of the blood, of course, the pulse rate, the heart rate, breathing rate, which is also integrated or part of this PPG signal, so the optical signal, what we are achieving. The moment we're running several blood pressure studies to be able to extract there as well blood pressure and changes of this blood pressure, activity analysis, as we are also having accelerometers, so you see the movement of the head of the test person or the patient, and then building on the vital parameters what we are collecting, deviation scores, like for example the new the early warning score, the Manchester score, something like that, and of course some other parameters like heart rate variability. So at the moment, our devices are used in many different applications. On the one side, remote patient monitoring. This is where we are coming from. So the patient is at home. The data is going in real time to the clinic. So you see here a picture from during Corona, where at the Technical University, they used it for monitoring COVID patients. And they were risk patients. Normally, they should go to the clinic, and they managed it that these patients were able to stay at home. And only if something was getting worse, they were calling the ambulance, and only then this patient was going to the clinic. It was also used for several oncology patients during a chemotherapy or immune therapy. So it was really to monitor them. They can stay at home. They don't have to go to the clinic every second day. So it's this typical monitoring. Then, of course, inside the clinic, they use it for monitoring, sometimes with some specific applications like cardiac surgeries or heart surgeries where they cooling down the patient a lot, but also during ICU and some other specific topics, and mainly on the normal ward where they want to monitor the patient. As I said, so Cosinus is based on two columns. The one thing is the in-ear sensor, and the other one is transmitting the data. So inside the ear canal, we have this big advantage that we're measuring close to the brain, so in a very central position. So we're measuring there the oxygen saturation, which is going to the brain through the arteries. We are able to measure core temperature, and even for some specific use cases in the emergency area, we are even able to measure when the patient is under shock or centralized. Everything with one small device. It's well validated in several different studies, and where it now matters, and that's why we were very pleased that we were invited to this lunch talk today. It's because there's a remote patient monitoring, which is our where we're coming from, and now we have many applications in the emergency area with helicopters and with mountain rescue. But the remote patient monitoring, this is mainly what's now used in clinical studies, but also biotech studies, pharmaceutical studies, phase 1, phase 2, even to phase 4, where it makes sense that you need an automatic acquisition of the vital parameters of the test person. You want to see it in real time. You need all this data. You have direct access to it. And like I said, so for remote patient monitoring, the devices and the whole solution was built that the patient is able to apply the sensor, that you also get good data, even if the patient is only applying it himself, the devices, and so on. So that's why it really makes sense in all kind of studies like this. And then, of course, the remote patient monitoring means you have in real time overview about all patients or test persons. You have the current values, you see the trends, and you see even this in-depth view as we are able to transmit 200 data sets per second. And this is, of course, reducing cost of patients a lot. Several publications about that, how to deal with these digital endpoints and how they will change these clinical studies and the procedures. And we are pleased that our device and our solution is there, part of that. And like I said, so it's used in several applications at the moment. The good thing is it's really the acceptance. It's very high. Everybody knows the speakers from, if you hear music with speakers, sometimes it will hurt you because all the speakers need to block the sound. In our case, we don't block the sounds, which means the ear sensor is very comfortable. We had several collaborations with hearing aids, which are mainly optimizing the devices for long, that you can wear it very long. And the studies which were conducted with our devices, they were the average wearing time between 14 hours up to 23, nearly the whole day. Now it's also running studies where they use it during night, so it can sleep with the device. So if you need this data during night, you can also use it. And of course, it's possible and acceptable for older people And here's a small mistake. It's not smaller than 59%, it's 5%, where the retention rate. And that's all from my side, and I'm happy to answer all kind of questions.
Thank you very much. Yes, you told that already a little bit. Our interest, let's say, from the biotechnology side is to use these technology for clinical studies. So is it already well accepted to use it in clinical studies to map digital endpoints in the different phases, or what do you have to do for that?
Yeah, so on the one side, we have the medical certification, which is the starting point that it's able to be used in this studies. We have this now since 1 year roundabout. So we are now in the discussions with several pharmaceutical studies where they want to use it. But it was used, like I said, for example, a very good study here also at the, I think it was Technical University of Munich. They used it during this chemotherapy where the patients should wear it 3 times a day for, I think, half an hour or something like that. And they were using it much more than they should because they want to have this security. They want to see somebody's taking care about me in this very stressful situation. You're doing a chemotherapy. So they really used it much more. And like I said, now it's we are talking with several CROs and pharmaceutical companies who are planning to perform studies with that. But it's taking, in our market, it's taking always time.
So how is that remote working? Do I have to be? Do I have to have a second device with me, which then sends the data into a cloud, or is it via a smartphone, or?
Yeah, so it's both. Both is possible. Of course, you need the in-ear sensor where you get the data, and then it's depending on the study. Sometimes we use gateways, which are a black box you only plug in into. It only needs power, and then it's working. So it means, so for example, elderly people, they don't know if they have Wi-Fi, they don't know the Wi-Fi password, and sometimes they don't have a smartphone or something like that. So they use the small gateway, which is then sending, so it's getting the data via Bluetooth from the in-ear sensors and then sending it via mobile network to our server. Everything GDPR conform, everything pseudonymized, and so on. And then it's going to our server where you have access to it. And beside the gateway, of course, we also have smartphone applications which can do the same. And then it's really depending on the study, the use case, which is better, or if you use both or something like that.
One question that came up in my mind as you wrote about working with elderly people, how do you deal with if they don't hear well and they have hearing aids? How can you combine that?
It is on the one side, of course, you can only put one device in the ear. So this is the one thing. The other thing is we also have collaborations with hearing aid companies as well as with people who are supplying hearing aid companies. So there are also some things coming where hearing aids are able to measure with our technology.
A combination of.
Yeah.
Okay.
But of course, you have only 2 ear canals if they are blocked. Yeah. it's not possible.
I think you told that as well, that your device has all necessary interfaces that the data from the cosinus system can be transferred into clinic systems to be, well, analyzed, used further on.
Yeah, so this is our approach. We know that, yeah, many other companies, they have their own solution for everything, and it's a closed system. So we are in this case very open. And as we are developing all of these steps from in-ear sensors via the gateways to the server, we also have access to all these interfaces. So that's why we are connecting to existing systems as we are able to do that. If they are open the interface for us, we are able to connect it. And then, of course, you have it interoperable with your current system. It's depending on what you're using. And it's sometimes even that our in-ear sensors are sending the data via Bluetooth to existing applications which are not coming for us. So to be able to be as flexible as possible to connect the data or to get all this data in the current system and not, not inventing the wheel again.
So again, a question about your business model. Who is paying?
It's depending on the use case. On the one side, in this emergency area, it's the helicopter companies or the mountain rescue organizations. They are buying the devices. They are using, having a license for using software for that. The same, more or less the same inside the clinics, monitoring there. Remote patient monitoring, it's in Germany a little bit difficult. It's better running in other European countries like the Nordics and so on. And of course, with for clinical or not pharmaceutical studies and so on, then it's mainly the CROs. On the one side, it's all the time buying or renting the hardware, so the in-ear sensors, and then of course, depending on what you need, a license fee for the service, getting the data wherever you need it.
Okay, thank you. Can I please ask the other two speakers to show up again for the last minute or two? But maybe to all, what are currently the biggest challenges with respect to AI development in biotech or biopharma?
Shall I start? Okay. Or you want to start? Okay.
Yeah, please go ahead.
Yeah. So in our case, it's really that yeah, getting this good data, good labeled data, it's the main starting point. And there are so many examples where it's the algorithms are trained for something specific, and then you use it for general things, and then it's not working. And there are, let's say, very famous mistakes where people with darker skin are not recognized, and it's not related to biotech, but there are really some things like this. And this is, you can put the same example overall. That's all the time the same. If you're not able to train the data, or you have good enough data, and then at the end the algorithm is not working. And there's this. Everybody thinks if I have enough data, I put it in, do some magic, and then I have the truth at the end. That's not working, and this is, I think, what's a challenge.
Yeah, I can second that actually. Access to good data, good labeled data is definitely one of the most important challenges. Apart from that, I could say for our specific case, building the computational infrastructure is one of the challenges, because for being to be useful in the clinic, we need to be able to process this data in real time. And when you're working with video data, sequential image data, you need to transfer this data into some where you can do heavy computations and then transfer the results back into the clinic. This is also one of the challenges. Yeah.
So you mean the infrastructure in the clinics?
Yeah,
the IT infrastructure in the clinics.
Yes. One of the challenges is like not all the IT infrastructure is up for that, and also from our point of view, we also need to build a good infrastructure in the cloud where we can process this data as well.
Concerning the data, is it because the data you need is not existing, or is it because it's not available for different reasons?
For our case, the data is existing, of course, but it is, of course, since it is a medical data, it is strictly protected, and you need to have also the proper infrastructure also to handle the legal side of the process. And also there's a huge diversity in the population as well, so you need to be able to capture very different data from the different populations as well, and this is one of the things that challenges it, I would say.
Okay, so many thanks again to the speakers for their interesting insights. And many thanks to you all for listening and watching. I hope you will be back next time. In 2 months, we will have the next lunch talk. And don't forget to participate in our event, the BioConnect. See you again. Bye.
Thank you.
Bye.
Bye.
Thank you. Bye.